My name is Andy Sayler, and I'm going to be presenting on Custos, Increasing Security with Secret Storage as a Service. This is joint work with my advisor, Dirk Grunwald. We're locals. We're from just up the road at University of Colorado. So welcome to Colorado, everyone, for those of you that aren't from here. Hopefully you enjoy it. Get away from Broomfield a little bit. The other areas around here are nice. But on to the topic at hand, I want to kind of start by asking this question of where do we store data today? And I think the answer for many of us is kind of in this myriad of cloud-based third-party services, right? So we're storing our data on places like Dropbox, storing documents on things like Google Drive, photos, etc. on Facebook, our bulk of our lives communications on Gmail. There are all of these kind of third-party cloud-based services, and that tends to be where many of us are entrusting the bulk of our data in the 21st century in the age of the cloud. And all of this begs a question, what does this actually mean in terms of trust, right? Does this mean that I have to fully trust Facebook with all my photos? Does this mean I have to fully trust Google with all my communication, right? How much do I trust these companies? Do I have a choice? Is the choice not use them at all or trust them entirety? I mean, is there any middle ground here? What's the trust model really look like? Kind of regardless of how much you trust the companies themselves, thanks to Edward Snowden et al., we know that the US government has an interest in the data you are storing with these companies, probably other governments as well, various other organizations, anyone who can subpoena these companies might be able to get a copy of your data, and that may not be the ideal sharing model that we're looking for, right? That may not really be what we want. We might prefer a little bit more control over our data and who has access to it. There's also the issue of security. By passing our data off to all these companies, we're largely giving up direct control over the security of that data, right? I cannot control how secure Google keeps their data centers. I'm simply forced to trust that Google is, in good effort, keeping all of my data secure, or Facebook or Dropbox or what have you. And most of the time, that may be a fair assumption to make. These companies do have a vested interest in keeping things secure, but we have seen recent things like the Heartbleed bug. We know mistakes get made, right? And regardless of how good of a job we think companies doing at security, there are going to be other Heartbleeds, right? There's shell shock last week. There are always going to be bugs. There are going to be mistakes. There's going to be the potential for your data to get leaked. And the more services you store it on, the more places it's going to be. The larger that attack surface is, the higher the likelihood that something will get out that you did not necessarily intend to get out. So this kind of begs the question, how can we control and protect our data in this age of cloud services, of third-party services, of these modern sharing-based use cases and multiple devices that we need to sync data across? We could go back to the old model, right? I can keep all of my data on a desktop in a locked room, in an air-gapped machine, not connected to the internet, and none of us would ever get anything done. It'd be very secure, it'd be great, my data would never get leaked, and I wouldn't care whether or not Heartbleed happened every other week because I wouldn't even have an internet connection. But that's not practical. So the real question we want to ask here is how can we kind of increase the security of our data while still acknowledging the fact that we're going to need to store it with third parties. We're going to need to spread it across devices, right? These are simply the nature of the way that we're expected to use data today. So potentially the answer lies in client-side encryption, right? There are companies that propose this. You have things like Spider Oak that build their entire business model around client-side encryption and trying to secure everything on the client such that the only thing you're ever handing to these third-party services is the encrypted ciphertext itself, right? You're never actually giving Dropbox, Google, etc. a copy of the plain text data. You are merely giving them copies of the encrypted data and assuming the encryption works, there's nothing they can do with that that would reveal information about the underlying data itself. So this may be fine, this could be a valid way of doing things, but we're missing part of this picture, right? Underneath all of this, we haven't really answered the underlying question, and that's what do we do with the encryption keys, right? There are keys at play here. There are secrets that are involved in making this encryption work, either to ensure we can encrypt it, to later allow us to decrypt it, whether you're doing it symmetrically like this diagram would indicate, or you're using some form of asymmetric crypto, you still have private keys. There are keys that you need to make this system work, and the question of what we do with these keys really lies at the heart of what we can accomplish in a system like this. We obviously can't just give the keys to Dropbox as well. That would largely subvert the purpose of doing client-side encryption in the first place. Maybe I just keep the keys locally, but then what problems does that introduce, right? Does Dropbox still work if I keep all the keys on a local flash drive? What's Dropbox really giving me at that point? So we think there's a lot of interesting questions that kind of come down to this issue of how do you securely manage these keys and do so in a manner that's both flexible enough to support all these use cases, but also secure enough to provide you with guarantees beyond what you would without doing this in the first place. So we've built Custos. Custos is Latin for guard, for those of us that studied computer science and not classics. And it's a key storage as a service architecture is what we're calling it. So by key storage as a service, it's really a subset of a larger architecture that we refer to as secret storage as a service. In this case, the secrets we're storing happen to be encryption keys, symmetric or private. And that's largely what this work was focused on. You can imagine extensions of this work that would look at more general purpose type secret storage and the properties you would want in something like that. But here we're focusing merely on encryption keys and the cryptographic primitives that they can protect. So instead of having this kind of ephemeral, well, great, I'm doing client-side encryption, but I haven't really answered the real hard question here, our answer to the question is, we have this dedicated service, and it's going to handle storing our keys. And in order to make this work, and in order to give this the properties we want, we have a few core features that we feel any kind of successful secret storage or key storage as a service architecture needs to implement, and that's what we've tried to implement in Custos. So in particular, we feel it's important for this to be a logically centralized service, meaning that it's accessible from a variety of devices, accessible from a variety of locations, potentially shareable with other users. There is a logically centralized point that we can reasonably expect various clients to be able to access with the appropriate access control semantics. And we'll get more into what this means momentarily. But we also feel it's going to be important for it to have a fairly flexible access control model. Obviously, when you're talking about encryption, you're talking about encryption keys, there's really a range of data that we might want to protect from things that only I, myself, should ever have access to, and thus that key's never going to need to be shared, and I can protect it with passphrases or further cryptographic primitives, what have you. But there's also going to be stuff that I do want to share, right? If I want to encrypt a bunch of pictures and send them to my grandmother, that's obviously going to be a key that needs to have an access control model that allows multiple people to have access to it. There's a bunch of different situations and that we're going to need to be able to support, and we need the flexibility to support those. So we'll get more into this as well. The final thing that we feel is important for any kind of a centralized key storage service like this to have is a strong auditing framework, in particular because what it can tell us about revocation semantics. So, once we give someone access to the underlying plain text data, we can't really reliably get it back. At least not ethically. And what it actually means to try to revoke something is largely dependent upon the history of how that data has been used in the past. So having a strong auditing framework that allows us to kind of tell how it's been used in the past and thus tells us something about what it means to cut off someone's access at a certain point of time is going to be important to the wider ecosystem here. So diving into these kind of one at a time a little bit, centralized secret storage. So if we just take, for example, I've alluded to this multi-device file sync use case, right? So this is something we've all probably done. You have a desktop that has some file on it, and you use a service like Dropbox to share that file to automatically sync it with your other devices, your laptop, your phone, your server, what have you, right? We have a bunch of devices, we use them, and it's nice to be able to automatically have files synced across them. So this is fine, but if we want to move to a situation where we're not just giving Dropbox a plain text copy of our data, and we want to use something like client-side encryption, again, what does this mean? So we can encrypt something on the desktop. The key is going to be stored on the desktop by default, if you're using most of these kind of existing systems out there. We can pass Dropbox a copy of the encrypted file. That's good. Dropbox now doesn't have access to the underlying data. But neither does our laptop, right? Our key's still sitting over on the desktop, right? How are we going to actually decrypt something on the laptop if the key only exists where we originally encrypted it? There's some things we could do here, right? I can manually take this key and stick it on a USB drive and distribute it on other machines. I could email it to myself and encrypt it using some other password. I mean, there are workarounds, but they're largely difficult to use or they defeat the purpose in the first place. If I'm taking a USB drive around to every device to distribute my encryption keys, why don't I need Dropbox? I should have just put the file on that USB drive in the first place and avoided the whole problem. So we get around this by using something like Custos, where now after the desktop encrypts the file, it passes the key off to the centralized server, and now we can set up access control rules on the server that says, well, the laptop should be able to access this, the desktop should be able to access this. I can continue to use, name your sync service here to distribute the encrypted file, and I can rely on this kind of centralized key store to allow any device that needs to decrypt the file to get that access to the keys it would need to do that. You can imagine a number of other situations where this kind of centralized nature would come in handy, something like a managed SSH agent, where you could have a corporately coordinated set of SSH authentication keys that are managed from a central location that are automatically distributed to various people. Things like an SSL processing backend, where you have a bunch of VMs that you want to spin up as your web front end, and they all need access to your SSL keys. You can use Puppet to manually copy those across, but if you want something more secure with more degrees of control, you could have this centralized backend controlling your SSL keys and providing access to any front end web server that would need that. And I'm sure there's a myriad of other use cases here you could dive into as well. So in Custos, the way we kind of attain the centralized secret storage is Custos is a client-server model. So we have this server that's in charge of actually storing the keys and the number of clients. On the server, we have this underlying secret store. We're kind of using some commodity off-the-shelf storage type backends right now, various key value storage backends. But then you also have applications on the clients that are going to want to get access to these keys. And in particular, the way we do it is we provide a RESTful API that gives them the kind of specific API calls you would expect. The paper gets into all the details, but things like the ability to request a key, to create a new key, to delete keys, to look up the access logs on the keys, to manipulate the access control parameters for a given key, so on and so forth. So this still does beg this question of trust, right? Is all we've really done here just changed who we have to trust? Now maybe I'm not trusting Dropbox anymore, but if I'm handing my key off to some other third party, I need some degree of trust of them. And maybe that's no better. I don't trust Dropbox, but I have to trust, Custos provider X or what have you. So I would argue that we're still better off than we were before, simply because at least there's not a single entity that now has access to our data, right? We would now at least have to have Custos provider and Dropbox collude to actually get back to the plain text data. But even if you're not comfortable with that, we can do better. We don't actually have to have a single provider. We've had clients, we've played around with having clients employ things like Shamir secret sharing to basically shard keys across multiple providers, such that now you take your key, you use some information theoretically secure secret sharing scheme, Shamir or something else, to basically split that key up and to distribute it across a set of providers, such that now any single provider doesn't have the necessary amount of information to decrypt your data. All of these providers would have to collude together to reassemble your key and then also collude with where you're actually storing the data to decrypt whatever you had underneath. So if one provider gets attacked, if one provider gets subpoenaed, so on and so forth, their portion of the key doesn't give them enough information to actually screw you over. And you can imagine, basing on how paranoid you are, how far you want to shard this up, how much you're willing to pay each month to these various providers to buy you this extra degree of security. This does have an additional benefit, and that's one of availability. Most secret sharing schemes are n-choose k schemes, such that we can divvy up our secret into 5 parts, but we only need 3 to reassemble it. And that way, if 2 of these providers go out of business or are down temporarily, we can still get access to our data, right? We can assemble it from the remaining shares. And again, given what the appropriate split is for a given situation, the trade-off between availability and security and what you're looking for can largely be left up to the client, because this can all be performed client side. The server itself doesn't know the difference between storing part of a key or storing the entire key. So that's centralized secret storage. The next kind of key component we have is this flexible access control model. So again, an example of where flexible access control would come in handy. You can think of something like you need to boot up a server in a data center, right? Pretty simple use case. You get onto your network UPS, you turn on the power switch for that server, and the server comes on. Life's good. But what if you want to use full disk encryption, right? What if you want to secure against the data center getting broken into, someone walking off with your server, all of these other situations where physical access, is not going to be secure in and of itself. You need security beyond that. So full disk encryption, the way you traditionally do this, right, is you have some key that is stored on the machine as well, but you password protect the key. If you didn't, it would kind of defeat the purpose of using full disk encryption in the first place. But if you're password protecting a key, that means you need a human there when you boot it. And that human has to provide a password. That password is going to unlock the key. And now our server is going to boot. Well, try calling up Amazon and telling them you want to walk into their data center so you can type in the password to boot your server with full disk encryption. They're going to laugh at you. So you don't have a human, you don't have a password, you don't have a key, and you really can't use full disk encryption in this kind of a situation where you lack physical access. There are systems, you could argue you could have a remote hands kind of system where it's going to send your password over the network, and fine. There are workarounds here, but none of them are all that clean, none of them are necessarily all that secure. What we would prefer is, if instead of storing the key locally and protecting it with the password, let's hand it off to a dedicated server where we can actually put some good access control rules in front of it, such that now we could have rules saying, I want this key to be accessible this time of day from this specific IP range, and maybe that's the end of it. The server boots up. As long as it's happening during a specific time, the request is coming from a certain IP range, I can provide a copy of the key, the server can boot. You could add a number of other things here. I could have it literally send me a text message every time it boots, and I could provide it the password that way. The point is, we want to ensure the flexibility to kind of allow you to implement these various use cases that might be necessary. Again, other situations where this flexibility would be handy, a backup system, same kind of deal. You might want some kind of automated process that needs certain degrees of access in certain situations. We want the flexibility to be able to provide that while also keeping limits as well. Things like time-limited sharing, you want to share files with someone, but you don't want them to be able to access it before a certain date or something like that. We want the flexibility to be able to express these semantics, and a range of other situations where just having a real flexible access control mechanism will be handy. Excuse me. So in Custos, the way we implement this is through a couple of subsystems. We have the access control system, which actually implements all of the underlying access control semantics. And then we also have this authentication subsystem, which is in charge of verifying various authentication primitives. The authentication subsystem is plugin based, similar to something like PAM, such that it can support a wide range of authentication primitives. We provide a few in our prototype, but the idea is that you should be able to extend this on your own with other authentication primitives that we didn't think of or that are unique to your situation, what have you. In particular, the way the access control model in Custos works is Custos has various objects. The most common object, and the one we're kind of referring to here, is the secret object itself. This would be the underlying encryption key that you're trying to protect. And associated with each object, we have what's called an access control specification, where this is just a list of one or more permissions that are related to what you could do with that object. Then within each of these permissions, we use what are called access control chains that are ordered lists of authentication attributes. So because this is just a bunch of boxes, to make it a little bit more specific, if we pretend this is the read permission, right? So this is the permission for me to read this secret, to get a copy of this encryption key. And we say this access control chain requires it's looking for a username followed by a specific IP address followed by a specific password. As long as I can provide the right username coming from the correct IP address, with the specific password, I am granted access to this read permission. I can read the secret. Obviously, there's other permissions. The exact permissions differ by the type of object, but read, update, delete, so on and so forth. There's also, you can have multiple access control chains per permission, such that as long as I can satisfy one chain, I can gain access to that permission. So we found this to be a fairly flexible system. It allows you to express quite a bit of semantic intent. Coupled that with the fact that the authentication attributes themselves are plugin based. So not only do I kind of have this somewhat flexible framework, but I have a lot of flexibility in what I can use for the actual authentication attributes at each point. Built into the system, we have some basic stuff. We have explicit attributes, things the server's just automatically going to know about an incoming request, the IP address it came from, the time it came in, as well as implicit attributes, things the user might provide, passwords, user IDs, various cryptographic authentication protocols in the user half of that exchange, so on and so forth. But both these are plugin based, and they're designed to make it easy to be extended if you have some other authentication primitive. You want to add two-factor authentication, if you want it to text you every time someone tries to access something and you have to text back a specific response for that to continue. The idea is to encourage flexibility and extensibility. So that's kind of the basics of the access control model in Custos. The final key component we see as being part of Custos or part of this more generic key storage as a service type paradigm in general is this example of auditing and the ability to have that tell you something interesting about what it means to revoke data. So if we look at another example, we have a situation here, we'll call him Bob, where we have a set of files, we stuck them on a flash drive and we gave them to Bob. We encrypted them first because if Bob drops the flash drive in the parking lot, we'd rather not anyone can get to the files. But obviously our intent is for Bob to access these, which means we had to give him the key too. We had to either give him the password, we had to somehow, maybe we signed it with his public key or what have you, or we encrypted with his public key, what have you. We had to give Bob the ability to access the files, which means when we fire Bob, we can't really take any of that back, right? And we could ask Bob to give us back the key or to give us back the files, but that's meaningless. For all we know, he's already decrypted them all, he's made copies of them, he's printed them off, he's shipped them off to his collaborator someplace else. We really don't have any direct control over this once we give it away the first time. There's no way to reliably get it back. So we can change that a little bit if instead of ever giving Bob the key, we just give Bob a copy of the files, but then we keep the key on a centralized server, something like Custos. And in particular, we'll split this out so each key file has its own key. This is merely buying us granularity of access control. This way we can control exactly what he's accessed. And now, as before, when Bob wants to decrypt the green file, he just has to ask the server for the green key. As long as Bob's a user in good standing and he can satisfy the appropriate access control chain, prove it is Bob, or whatever hurdles we put in place, he can get the green key, he can decrypt the green file. But now when we decide to cut off Bob's access, we have a single point at which we can do that. We can revoke access. And at this point, Bob should not be able to access anything he hasn't already decrypted, that he hasn't already pulled the key for. Which does beg the question, what has Bob actually pulled the key for? And that's where having these kind of high-quality audit logs come in handy, where now we could look through something like this and we can go, oh, this picture isn't actually accurate. Bob grabbed a copy of the blue key last week, so even after we cut off his access, maybe he made a copy of that key locally, he could still potentially access that file. The pink file, on the other hand, though, we know with absolute certainty that there's no way he's ever going to be able to access after we revoked access. He never grabbed a copy of the pink key prior to revoking access. We at least have this log that can tell us something about Bob's access was revoked on Thursday, July 9th at 3 p.m. What does that mean? And we can say, well, that means he's definitely accessed the green file, he's probably accessed the blue file, but there's no way he will ever access the pink file. So in Custos, this is implemented again with kind of its own little subsystem that deals with keeping track of these access. It's basically a high-quality logging system. But in particular, it also puts an API in front of these logs that allows you to extend it and do things like revocation analysis that we were just talking about, be able to pull a copy of these logs and use it to compute what it means to do something at a certain time. You can imagine also plugging these logs into something like an existing intrusion detection system, run them through Snort, look for suspicious access patterns. You now have a centralized point at which you can do that. The NSA might have benefited from something like this a couple of years ago. And if you're in like a compliance-heavy environment, you could obviously use these as a proxy for certain kinds of or for compliance with certain regulations. If you have a regulation that says you have to monitor access to certain types of data, well, that might be hard to do when that data is spread off across all these devices. But if you keep the data encrypted and instead you just worry about monitoring access to kind of this centralized point that you would have to pass through to get the necessary keys to decrypt the data, that might be easier to do than monitoring all the data at the endpoints at which it's used itself. So we have built a Custos prototype. It basically involves the Custos server plus this client application that we call EncryptFS. It's only like the 5th or 6th EncryptFS in the research literature at this point, but yay for creative naming. It is a Custos-backed encrypted file system. So essentially what we have is we have this Custos server. That's where all the magic happens in terms of that's where we store the keys, that's where we implement these access control specifications, that's where we implement things like logging, that's where the API is implemented. And then just to prove this all out, we built this little fuse-based encrypted file system. It's an overlay file system, so it sits on top of some other existing storage device and provides transparent encryption as far as the user is concerned. But unlike most existing encrypted file systems, this plugs all of its key management directly into Custos, meaning that whenever it encrypts a file, it is saving the key to Custos and not keeping a copy locally. When it needs to decrypt a file, it's pulling a copy from Custos. What this also means is we're largely handing a lot of the access control semantics for the files themselves off to Custos as well, because now that this is just negotiating keys for us in between, if we want to block someone's access to a file, we can do it by blocking the access to their key in Custos. The other nice thing this has allowed us to do is, we can run something like this on top of an existing Dropbox folder. We're working on some native Dropbox type implementations, which would be even prettier, but even right now, I can run this on top of Dropbox. Dropbox can get encrypted copies of all my data, and I can decrypt it from anywhere as long as I have access to my Custos server running on the internet, right? As long as it's turned on. I can just rely on this being accessible from a variety of endpoints, some of those nice use cases we saw earlier that allow me to continue using Dropbox as I kind of traditionally would, with just the added minor overhead of having to tell Custos, these devices should have access, these users should have access, and still making it all kind of work. So we've done some basic performance analysis of this. Obviously, it's a fuse-based file system, so it's in user space. The point here is not performance. The point is to prove it does not suck so badly that you wouldn't want to use something like this. In particular, the main hit you take is on latency. That would make sense. We're imposing an additional round trip to the Custos server every time we go to access a file. Throughput doesn't have that much effect because that's largely limited by the encryption process itself anyway. But we do have this extra overhead of having to go to the Custos server to get the key once per file operation. And that does slow you down a little bit, but if you're already using something like Dropbox, this is not your bottleneck. It's not really, we don't really care. So in terms of current and future work, we're working on building out additional client applications. So we're currently working on an SSH-based key manager that would kind of allow us to have this centralized corporate access to a set of SSH authentication keys. We're also working on building like a PKCS11 compliant SSL processor that uses Custos as the backend. So, this would be a mitigation of something like Heartbleed. Now, if you have a dedicated server that's performing your encryption, you're ensuring that your key's never stored in the same memory space as your end user application. So if something goes wrong with it, you don't start leaking key material through your memory leak. And some other applications we're playing with as well, a more directly integrated Dropbox client instead of just hacking it on top with Fuse. We're also looking for better management of secret sharing. So like I said, secret sharing can largely be handled from the client side right now, but that poses some management difficulties. In particular, if you're sharding your secrets on the client side, Now when you want to revoke something, you have to remember where all the different providers you stored it with. You have to go there and manually revoke all the different parts. We would like to put put a nicer interface in front of that kind of stuff to make it easier for the end user to kind of manage the sharding without having to think about the fact that they now have their data stored in multiple locations. And we're looking at what else we can do with kind of this log and heuristic analysis. So we have these loggings. Obviously, there are many kind of log analysis projects out there, and we're looking at how those could be integrated, how ideas from those could be adopted to kind of leverage these logs to give us more information about the underlying system or allow us to more intelligently analyze what's happening to spot attacks, so on and so forth. So Custos is our attempt at building this key storage as a service architecture that offers centralized secret storage, flexible access control, and these auditing and revocation semantics. And our hope is that this will allow us to use things like client-side encryption in more flexible situations to apply it to a wider range of applications than it might fit otherwise. We can kind of see key storage as a service becoming part of this wider cloud ecosystem where you have your storage provider, you have S3 or Dropbox or Google, you have your secret storage provider, name some company here that's implementing something like Custos, and then you have compute providers, so on and so forth. But we think there's a place in the cloud ecosystem for kind of this dedicated key storage and access management type entity. So thank you very much, and are there any questions?
Who maintain? Can you hear me? So who maintain the providers? So when you recover the key, so multiple providers should maintain different key shares. So who maintain the providers?
So, right now we obviously are our own provider because we're running our own prototypes and stuff.
Okay,
but the idea would be if something like this did become standardized, or you could imagine companies springing up who this is the sole service that they sell, right? And then your ability to pay them or your willingness to pay them is based upon how secure you think they are or what legal jurisdiction they happen to be located in. I mean, there's a lot of interesting market economics you could get into on why this might make sense from that perspective.
Yeah, and some of them can be compromised by attacker, right?
Yeah, potentially, but that's why you could potentially use ones, or you could pay someone twice as much to theoretically be half as likely.
Okay, yeah, just confirm this. Okay, so cool. So the second question is who produced the access control specification, the customer or the?
So that would be produced by the end user, or at least by the application the end user is using. How best to integrate that with kind of existing systems? So right now, if I share something in Dropbox, I expect it to be shared. What would be nice if I shared something in Dropbox, it could both tell Dropbox it should be shared, but then also talk to the Custos server and set up the appropriate rules for that. So, we haven't dived in how the best UI to wrap in front of that, but yeah, the idea would be that the end user has control over that.
Yeah, so one concern is I think, so based on my understanding to the access control specification, I think it's kind of hard for customer to write such a specification in practice. So this is just a concern.
Yeah, no, and I agree that is absolutely a concern. Whether or not this does provide flexibility, but with that potentially comes complexity, and how best to manage that in a manner that reduces the likelihood of misconfiguring something. It's an open question. It's something we're looking at.
Okay, cool. So thanks.
Thank you.
Hi. So Landon Cox from Duke. So I really like the flexibility that Custos provides, but one question I have is with third-party software that accesses things like Dropbox. So one of the reasons that I like Dropbox is that I can share data across mobile apps. For example, I can edit PDFs and then I can store them in Dropbox and then get them from Dropbox and mail them somewhere else, right? So with NCAVS, you can transparently decrypt things because you can integrate key management with the file system. But it seems like that would be much harder with random third-party apps like mobile software. So I was wondering if you think that's fundamental or if you have a story for how you would handle that.
I mean, I don't think it's any more fundamental than, if you'd come here 10 years ago and someone's proposing Dropbox and you would stand up there and say, well, I have all these third-party apps that already have their own storage services, and how am I going to get them to implement with Dropbox as their lone option instead? So, I mean, I think our main argument for that is if you did, there is a good argument for something like this being standardized, right? Whether it's Custos or something else. But if you have a standardized interface and apps can just build this in, now when you sign into the app, not only do you give it your Dropbox username, but you tell it about whichever Custos providers you're using as well. And I think that's really the ideal, eventually. Easier said than done, right? But I think that would be the best answer to that kind of a question.
Yeah, I think that makes sense. Thanks.
Thank you.